Good evening, everyone. Welcome to the week 8 problem solving session for the course Matlab-Based Programming Lab in Chemical Engineering. We'll begin the session in 2 minutes. Let's wait for some more students to join the course. We'll begin the class in 2 minutes. So let's begin today's session. So this week, the problem that we were trying to do is a one-dimensional heat transfer reaction. So heat transfer process. So here we are considering a one-dimensional heated rod in which heat transfer takes place both by conduction and convection. So the schematic of the system is given like this. So here what we have is a rod, and imagine that one side of the rod is like maintained at T is equal to TA. Okay. And then that is where, and here we are taking the reference for the length of the road is x is equal to 0. And the other length of the road, other end of the road, we consider that x is equal to L, where L will be the length of the road. Okay. And then we have this end fixed temperature as TA. And due to conduction and convection, there will be heat loss or heat gain depending on what is the temperature at both the ends. And then what happens is we have here the temperature at the end of this heat, the temperature will be T equal to TB. So what we have also, there is one more information that is given to us, the ambient temperature. That is, there is convection that is happening from the road to the surroundings, and the surrounding temperature is maintained at T equal to T infinity. So we'll have to we'll have to formulate the equation in such a way that we can find the how the temperature is varying with respect to the length of the road. So what we have is we need to understand that here the temperature is TA and here the temperature is TB. So when x is equal to 1, what will be the temperature? X is equal to 2, what will be the temperature? So as you move along the length of the road, we should be able to find what the temperatures will be corresponding to it. So now these are the details that is given to in the problem. That is, this kind of system can be modeled using a following equation. D square T by dx square plus beta T infinity minus T is equal to 0. So this is a differential equation, but we need to identify what kind of differential equation it is. So here, if you see, what we are trying to understand is we are trying to understand the temperature gradient with respect to the length of the road. Okay. So what if not only along the length of the road, there will be temperature gradient also in the vertical. That is along the width of the road. But what we are doing is we are assuming that kind of temperature gradient is negligible, and we are only taking the temperature effects due to the length of the road. So here there is only one independent variable, which is the length of the road x. So since there is only one independent variable and we have the temperature, which is a dependent variable on it, so then what happens? We are dealing with an ordinary differential equation. It's not a partial differential equation. It's an ordinary differential equation because here we only have a single independent variable. Now that is why we have here d by d instead of dou by dou. So here we have a ordinary differential equation. Another thing that you have to observe is that in earlier classes we have seen ordinary differential equation, but here this is the second order ODE equation. So second order ODE equation, though we have not explicitly done in the recorded lectures, during solving the problems, we had done two questions where a second order ODE can be converted into two first order ODEs and it can be solved using the ODE solver like ODE 45 or ODE 15s. The only thing is you should be able to carefully convert the second order ODE to a first order ODE and use the inbuilt MATLAB solvers to solve it. So this is a second order ODE equation that is there. So what is capital T? Capital T is given as T of x, which is the temperature of the road at a particular location x. And we have the beta parameter which is given to us. Beta parameter will have the ratio of your conductive heat transfer to convective heat transfer. So that you will understand. So if you have gone to the recorded lectures, you already know what is the definition of beta. Otherwise, please take a moment to go refer what beta means. So here the beta value is explicitly given to you, which is equal to 0.05 meter minus 2, meter raised to minus 2. Now here we have the ambient temperature, and the ambient temperature is said to be 25 degrees Celsius. Further information that is given to us is the length of the road is equal to 10 meters. And what is the temperature? What is TA and TB? This is TA and TB. So here at x is equal to 0, your temperature, which is TA is equal to 25 degrees Celsius. And in the other end of the road where TB is there, that is since x is equal to L, we have the temperature to be equal to 750 degrees Celsius. So here this is 25 degrees Celsius, that is 750 degrees Celsius, and the ambient temperature is also 25 degrees Celsius. So this is the information that is given to us. Using this information, we should be able to solve this ODE equation. Okay. Now let us look at the sub questions that is expected from us to solve. So these are the problem statements. Determine the temperature profile along the length of the road. So this first part we already know. How do you get it? You have to directly solve the ODE equation. Then what happens? You will be getting for different x values, you will be getting the corresponding temperature values, T values. That is what you get as a solution when you are using any kind of ODE solvers in MATLAB. So that part is like pretty much clear. Just that you need to carefully convert that second order ODE to first order ODE. Then it's similar to what we have done in the previous classes. Next is analyze the effect of ambient temperature on the temperature profile. That is ambient temperature is this T infinity. Now what I do is the ambient temperature earlier it was set to be 25 degrees Celsius. Now I'm trying to vary my ambient temperature within a certain range. That is from minus 50 degrees Celsius to 200 degrees Celsius with all of the specifications remaining the same as those given above. So the only parameter that will be changing is the T ambient, which ranges from minus 50 degrees Celsius to 200 degrees Celsius. Next is repeat the above exercise for different values of beta. So here the beta value is given as 0.05 meter inverse square. Now we have to vary beta from 0 to 1 and see what will be the effect on the temperature profile that we see. And when you're doing this, we need to fix, when you're doing the third part of the question, we need to fix all of the parameters, including the T ambient to be a particular value. Okay, all of the parameters has to be fixed and only beta varies. Next, we have to compare and contrast the temperature profile for the following conditions. So there are boundary conditions that is given to us. Okay, so this is another important point which I missed. So here we have an ODE equation and we understood that it is a second order ODE equation because of d square by dx square. The next part of the equation, next part of the part is, so far we have always done ODE initial value problem. That is at time t equal to 0 or like potential at time t equal to 0 at the position x is equal to 0. We know what the parameters like the temperature or whatever it is, we know what is happening at the starting of the process. But here what we have is, we have two informations that is given to you. At x is equal to 0, you know that there's a particular value. And at the end of the road, at x is equal to L also, you have a particular value. And whatever type of method you try to solve or whatever theory that you use, this two values here, that is a boundary values, has to match exactly. So this makes this problem a ODE BVP problem or ordinary boundary value problem. So ODE boundary value problem has to be solved. So right now we are given whatever is given to us in the question is the temperature value that is given at the one end of the road and other end of the road. So these are the boundary conditions. Now what we have to do is we have to keep changing the boundary conditions and understand how the temperature profile change along the length of the road. So here first we have is the T at the beginning is 25 degrees Celsius itself, and T10 is given as 150 degree, which is the first problem that we try to solve. Now the second sub question is we are fixing the first end of the road remains at 25 degrees Celsius, but at the other end of the road, it's not the temperature, but the temperature gradient has to be 200 degrees Celsius per meter. So there is a difference here. And the other function, the other sub question is at the both at the end, both endpoints, that is even the starting and the end point, what we have is the gradient has to follow a certain value. That here the first dt by dx is x is equal to 0 has to be 0 degree Celsius per meter, and dt by dx at x is equal to 10 has to be 200 degrees Celsius per meter. So here these two gradients has to satisfy. So these are the sub questions. These are sub questions we need to answer. So first, let us see how the analytical solution will look like. You can like directly integrate and try to find the analytical solution. So what happens is when you directly integrate it, you will be getting an equation like this. Okay. And finally, what happens is since it's a double derivative, what will happen is we will have two integration constants. And for finding the two integration constant, you will have to apply the two boundary conditions one by one. And finally, you will be getting a solution like this. C1 e raised to minus C1 e raised to square beta x plus C2 e raised to minus square beta x minus t infinity. So this is the final analytical solution that you get by solving this ODE BVP problem. Do you have any doubts so far? Okay. So now from this solution, what do you understand? Here you know this is an exponential term, which is like a positive exponential term. Then you have like an exponential factor, which is negative. So here from this expression itself, you know that whatever you're trying to get will not be a linear solution. It will be a non-linear solution basically. Okay, so now let us see how to solve this ODE BVP problems. So before going into our question specifically, I'll just give you an example. So imagine we have a system like this. D square t by dx square is equal to gamma t minus 25. Okay, see, the parameters are different. I'm not talking about the solution, that question that we have seen before. This is a totally different question. I just wanted to give you an idea of how to solve this. So we have two boundary conditions that is given. At one end of the road, the temperature is 100 degrees Celsius, and the other end of the road is 25 degrees Celsius. So the first thing to do is you have to convert the second order ODE into first order ODE. How do you do it? So sorry for that, I had changed the variable. This was supposed to be x. Okay. Z and x is the same here. Sorry for that. So now d square t by dz square or dx square is equal to gamma t minus 25 at is x is, so let me just read it as x is equal to 0 is equal to 100, at x is equal to L, temperature is equal to 25. This information has been given to you. Now what you have to do is convert this part, that is d square t by dz square, into two ODEs. How do you do that? This is what we do. I've already explained it in the one of the previous sessions, but I'll do it once more. So what we do is we just say d, sorry, dt by d, here is it, okay, is equal to a new variable y. I'm calling this a new variable y. Now what happens? I take a derivative on both sides, okay, both on the RHS and the LHS. Now what happens is d square t, I take a derivative of both with respect to z, dz square is equal to dy by d z. Okay. Now what happens is this is one of the ODEs. Okay. And now for this ODE, what you do is, d square t by dz square is this term, right? So let us write that here is equal to gamma t minus 25. Okay. Now what happens? You take this portion as another ODE. So this becomes your first ODE and this becomes your second ODE. So this is how you do. You converted this second order ODE into two first order ODEs. So this is just d by dz. This is also just d by dz. So this is two ODEs, first order ODEs. But here your variable you're trying to solve is for temperature. Here you're trying to solve for y, which is nothing but your temperature gradient. So this is what you do. Now what you do is you try to solve for two variables. Earlier we were trying to solve for only t. Here you will have two variables. Okay. From the first equation you will get temperature, and the second equation you will be getting y, which is nothing but dt by dz. So right time being, let me just write y. Okay, I'll just write y here. So these are the two variables I'm looking for. T and y will be the variables I'm trying to solve for. So that's exactly what is happening here. We have here two variables, t and y. I'm calling the whole vector to be capital Y. Here, what is the small y? Small y is nothing but the gradient dt by dz. And you can write dy by dz, that is whatever I've written here, is equal to gamma t minus ta, where ta is nothing but 25. Okay, so this is how you convert a second order ODE into two first order ODEs. I hope this part is clear. Next, what you have to do is you need to somehow encode this boundary condition. Okay. So earlier, what we had is for the ODE solver, what we did is in the ODE 45 or ODE 15 years, what we try to do is we can give the initial guess. Okay. So, but that ODE solver, whatever we saw, ODE 45, ODE 15 years, and all those things, we can only use if it's an initial value problem. If it is a boundary value problem, we have a different solver altogether in Matlab, which is called as BVP5C. Okay. So in BVP5C and ODE 45 or those solvers, the only similar thing is if we have a second order ODE, in both the cases, you will have to convert into first order ODE so that you can solve it. Okay. But in ODE 45 or ODE 15 years, it does initial value problems and this does boundary value problems. So the way you encode the boundary values is slightly different here, and we'll understand how to encode them. So the first thing you have to do is the boundary conditions has to be written in a form that you have to write it in a form of an equation so that it equates to zero. For example, I have this boundary condition like this: t z equal to 0 is equal to 100, t z equal to l is equal to 25, right? Let me just bring this 100 to the other side and 25 to the other side. So it becomes t z equal to 0 minus 100 is equal to 0, and t z equal to l minus 25 equal to 0. And I'm calling this whole thing to be T0 and this whole thing to be T1. It's just giving a random variable to it. So now I have two boundary conditions. T0 minus 100 is equal to 0 and T1 minus 25 is equal to 0. Okay, so these two are my boundary conditions. Now how to code this boundary condition is a totally different thing. We'll try to do that. But I hope you understand that how we formulated this second order ODE to first order ODE and how we'll be coding the boundary condition. Okay, I hope that part is clear. So now, what is the mathematics behind it? So basically what you do is you will be using finite difference method. So in finite difference method means we have the second derivative, which can be approximated using the central differencing formula. This is how you formulate it. Just a second. Yeah. So this is how we formulate a second derivative with respect to finite differential. So that is, if we have a second order derivative like this, using central differential formula, it will be like this. So at a double derivative at xi, point will be equal to the function value at the next point, that next point in the grid, that is xi plus 1, minus 2 times the function value at that particular point, xi, plus the function value at the previous grid point, that is f of xi minus 1, divided by h square, where h square is the distance between the gridding. So that's what we do. If we have a total length, for example, here in our case, we have a road here. What we do is we do a finite gridding here like this. Okay. So this will be I, this will be I plus 1, and this will be I minus 1. Now what we are trying to do is, just a second. Okay. So this is how the finite differencing term looks like for a double derivative. Now what we have to do is we have to grid the entire length of the road, and write for every grid you write this equation. Okay, and then when you rearrange, you will be getting a matrix, and the matrix will have a coefficient matrix like this. It will have a constant matrix like this, and it will have a variable matrix like this. And the variable matrix will have T1, T2, Tn plus 1, where, sorry, I just removed the previous diagram which I drew. So that is, if you have a road like this, okay, this is 0 grid point. This is first grid point. This is the second grid point. Okay. So on like this, you're dividing. Okay. And then you will have the n plus 1 grid point. Sorry, n plus 1. You're dividing into n equal intervals. So here you have different grid points. The T0 is already known to us. Then we have T1, T2, T3 till the last value. Okay. So this is how we try to do this. Now to give you an example. So once you have all this data, if you have a coefficient matrix, if you have a matrix of all constants, if you have a vector of all constants, and if you have a vector of all the gradients, it will be of the form ay is equal to b. And what we need to find is this y, that is different value of the temperatures at different grid points. So what do you do? Y is equal to nothing but inverse of a multiplied by b. This we have already done. Okay, so that is the basic idea behind it. So how will the function looks like? So this is a kind of a function that we are trying to do. That is d square t by d z square equal to gamma t minus 25. You know what the initial temperature is, and you know what is the final temperature. Sorry, this is a numbering. Okay, it starts from 1 and it ends from n plus 1. So there are n intervals. So it doesn't start from t0. It is t1 to n plus 1. Now what I do is I try to write an equation at every point. T1 is known to me, so I can directly write T1 is equal to 100. At T2, I don't know what the value is. So what I do, I simplify this equation at T2. I write this part of the equation using this finite differencing formula. So that will be nothing but, remember, here I is 2. So I'll write T3 minus, so it will be like this. T3 minus 2 times T1, sorry, T3 minus 2 times T2 plus T1 divided by h square. So this will be this equation. T3 minus 2 times T2 plus T1 divided by h square is equal to whatever this there in the other side of the equation, that is gamma. Here T will be what? T will be T2 because I'm doing for this current grid point here. So that will be gamma T2 minus TA, where TA is nothing but 25. So here the h square term, I'm taking it to the other side. So this will be the first equation that I get here at the T2 grid point. Similarly, I write equation for here. T3, T4, and everywhere. At every grid point, I write the equation. Tn plus 1, I don't need any equation because I directly know what is the value there. So now when I keep on writing this equation, for example, at an ith grid point, it will look like this. Ti plus 1 minus 2 Ti plus Ti minus 1 divided by h square is equal to gamma Ta minus Ta. This h square I'm taking to the other side. So this will be the equation that I get. Now what I do is, okay, I write a matrix from this. So imagine my variables are T1, T2, T3 till T1, T2, T3 till Tn plus 1. That will be my this one. Okay. And my constant B matrix, B vector will have this part. H square gamma, H square, this part of this side. And my coefficient matrix will have basically whatever is the coefficient of each of these variables. You need to write it properly. So it's better that you take a pen and paper and try to do it manually so that you understand how this grid is formed. So once you have that with finite differencing, what you have to do is just invert this matrix value and multiply it with the constant matrix, and then you will be getting what is the temperature values. I hope this finite differencing thing is you guys understood. If you have any doubt, please do ask me right now. Okay. Now moving forward, basically this is what we'll be trying to do. So now we'll just go back to this question and see how this has been coded. How is the BVP 5C solver coded? So now just a second. So this is how we try to, I hope you can see the MATLAB screen. So this is how you're trying to do the first part of the question. That is find the temperature profile for the BVP using the BVP 5C solver. And again, in the recorded lectures, you have been asked what is the difference between BVP 5C, BVP 4C. There are several solvers available. So just for that, we'll just use the help of MATLAB and see how this works. Okay. So BVP5C is a MATLAB solver. It integrates a system of ordinary differential equation of the form y dash is equal to f of xy. So understands here it is given y dash, not y double dash. So it's basically it can only work with the first order ODE. So if you have like higher dimensional ODE, you have to convert it into a first order ODE on an interval a equal to b, subject to 2-point boundary condition. So it is only works with BVP problems, not initial value problems, and it has to be in such a way that the boundary condition you have to equate it to zero. So there are two inputs that has been given: ODE fun, which has the ODE functions, just like you do for the ODE 14, ODE for 45 and ODE 23 and all those things. And there should be BC fun, which is basically boundary conditions function, which will encode the functions wherever that are equated to zero. Those two functions has to be encoded here, and you will get a solution. And for a scalar x and a column vector y, ODE xy must return the column vector representing f of xy. Just like on the ODE solver, we will have a if we have two ODEs, you will make it as a column vector. The first equation and the second equation, you'll put it in a column vector. And the boundary conditions also, that function also must return a boundary vector. It also must return a column vector, where the first boundary condition will be the first row of the column, and the second boundary condition will be the second row of the column. And finally, you will be getting a sol int. Okay, this is also very important. That is, you have the ODE fun, the boundary conditions function, and then you have something called a sol initial. Basically, this is for initialization of the solution. So sol int is a structure with fields. That is, what we do is, remember this BVP5C works on like finite gridding system. So what we do is we have to tell BVP5C what is the gridding that I'm doing. That is basically you divide x from 0 to L by small gridding. So for that you can use linspace or something. The gridding distance, the h you are defining. So you're telling that x is my grid points that I'm using. Okay. And the y, and for corresponding to x, I have to give a particular initial guess for it. So some initial value you have to give so that the ODE solver can start working. So I'm assuming that there is like this much grid points. And at these grid points, my temperature has a particular initial value at all these grid points. And also my gradient of temperature. Since here we are solving for two values, two variables, and my gradient of temperature also has so and so initial values. So this is what we are trying to input. So now BVP5C will have the solution which is given here, out of which sol.x will give you the gridding that you took, and sol.y will give you the output that we have. So in our case, we'll have two outputs. In sol.y, it will have two outputs. It will have the temperature and also the temperature gradients. Okay, so here are the other things you can just go see how does it work. Okay. All the rest of the things you can just read. So this is what I've said here. Now let us go look at the code. Clear CLC. So what I do is, this is my function. Okay, this is whatever we saw in the syntax. That is solution will have the solution vector with me. Sol will have the solution vector with me. I'm using the keyword BVP5C, and it has three function handles. The first function handle is has to be the BVP function itself. That is the boundary. That is the ODE equations that I have. So first, let me look at BVP function. Just a second. Okay. So BVP function, what will happen is it will take the input and output values. Here, X is the grid point, that is the length of the road, the position, position along the road, and Y has two outputs. Okay. That is Y1 will correspond to temperature and Y2 will correspond to the temperature gradient. Why? Because that is how we have said in the basically here. See, basically here what we did is the first equation was the temperature, solves for temperature, and second equation solves for y, which is dt by dz. So the y will have two values. One is the temperature and other is the gradient of temperature. So here we are taking h. H is nothing but beta here. Okay, don't confuse this h by the gridding step size. Here h is the value of beta. And T infinity means it's the T infinity is given to in the question, that is 25 degrees Celsius converted to Kelvin, that is 298 Kelvin. And this is the equation, ODE equation. So the first part of the equation will be dt by dz. So basically here like this, just a second. So first we'll have dt, okay, dt by dx, sorry for the bad handwriting, is equal to y. And what is this y? Here in our case, this vector's second value, right? This vectors will have two values. One is the temperature, second is the y value in our question. So basically you will write this y is second entry. Okay. This y is second entry here. So that will be your y2. And the next part is dy by dz is equal to minus gamma t minus 25. So this is minus gamma, sorry, t minus gamma t infinity minus that particular temperature T. So that will be the Y values first entry. That is why it is given Y1 and Y2. This corresponds to this entry and this corresponds to the first entry, that is temperature. And you make sure you write it as a column vector. So basically this output should be a column vector giving the two ODEs. I hope this is clear. Now let us go to the first part of the question again. Now we have to look at the boundary function, BCFCN. So let me just open BCFCN. Here also it takes in two values, that is YA and YB. Okay. And let me make this very clear. In BCFCN, there will be two values, YA and YB, or you can name it any other variables also. But the first variable, YA corresponds to the entry, that the first boundary condition, but the first boundary, and YB corresponds to the last boundary, that is the other end of the road. And YA and YB, again, as we said, will have two entries. So this is something that is very tricky. You need to understand that. So let me just take some time to explain this. Okay. YA will have two entries here. Okay. That is T and Y, which is the gradient of T. And YB will also have two values, which is again T and Y. But something you need to keep in mind is that this is at X is equal to 0 and this is at X is equal to the last point L. So now when you're defining, so this is the how the Y and YB is defined. Okay. Now, if I'm telling that, okay, my temperature at one end has to be 25 degrees Celsius, which is 298 Kelvin, and the temperature at the other end has to be 750 degrees Celsius, which is 1023 Kelvin. That's what has been given here. How do I define it? I write in YA, the first entry, okay, this has to be 298, sorry, and here in this entry, this first entry has to be 1023, which is 750 degrees Celsius. Now, how do I code it? I'm telling in YA, the first entry has to be 298, and in YB, the first entry has to be 1024. Now, imagine like I shouldn't write just equal to, I should bring it to the other side and equate it to 0. That's how the function has to be written. So that is why you see this minus sign. I'm telling the first entry minus 298 equal to 0. So I write this function here. The equal to 0 is not required. Now I write the second entry's first. YB's first entry minus 1023 is equal to 0. So that is how I get the first equation, first two equations. So this will be the BC equations. Again, remember it has to be a column vector. The first entry will be the first boundary condition and the second entry will be the second boundary condition. So that will be the output of BC equation. Is this clear? Okay. Since we have cleared that part also, let me go to the another. Okay, thus initialization of the solution. So for initialization of the solution, as I said earlier, first we have to create a gridding. So right now I'm telling that my length of the road is 15. L is equal to 15. What I'm doing is I'm trying to grid it. I make like, sorry, my length of the road is 10. If I remember correctly, my length of the road. Let me just check it once again. Yeah, the length of the road is 10. I'm trying to divide it into 15 grid points. So for that, I can use linspace, which is I give the initial point, I give the starting point, I give the number of grid points. So I'll just run this command for you. So basically, if you see here, there will be like 15 entry points will be there, starting from 0, and it will go up to the last length 10. And the spacing, basically, it will be automatic. It will be equal spacing when you use lin spacing, and it will be all it will be calculated by MATLAB itself. So I'm having 15 grid points when I'm using this. This is the mesh I'm trying to use. If you want a more refined mesh, you can increase this 15 to like 30, 50, 100, or whatever you want to if you want to increase the mesh size. Now, what I do is I try to initialize the values at this mesh. Remember, at this mesh, at every grid point, I have to initialize two values. One is t value and also the gradient of t, which is the small letter y we are using right here. So how do you initialize that? For that, I'm trying to use something called as this function. This is a function that is written. It's not a keyword. You can give any other name to it. Right now, I'm just calling it guess. So this is a guess function. And I'm telling that whatever the grid point value is, I am taking the first value, which is, remember, again, this order of the variable is very, very important. Here, remember, the first entry will corresponds to t, and the second entry corresponds to y, which is nothing but dt by dz. So when you give any initial condition, it has to make sense. So whatever the function is here, the gradient of that function should come here. Only then it will be physically meaningful, right? So I'm writing my first initial guess. You can assume anything, but here for time, for like having an easy equation, I'm telling that temperature, let it be sin x. And what will be y, which is the gradient of temperature, right? So the gradient will be cos x. So this will vary according to what kind of the grid points x value. Okay. So here, this is how I give. Again, this has to be a column vector. Now what I do is, this is the function, right? I have to evaluate, I have to get a numerical value at all these points, just not the functional form. So for that, I use this one. I use a function. This is called as BVP in INIT, which is an inbuilt MATLAB function, which is used to initialize the grid points. What I do is this is how I do. I give the meshing that is there, and I give what kind of function I should initialize it to. So if I run this function, basically, I'll show you here. I'll get a structure like this. Okay, this is how the solution works. And in the solution, the solver is this. I have a x value, which is basically the grid that I saw. Okay, that is this x mesh and the sol, this both are the same thing. Okay. And in the sol INIT, I have something called as y. This is the output values initialization. And here the first row corresponds to temperature and the second row corresponds to the gradient value. Okay, since it is a function of x, that is why you will see the different values. So what is sine 0? You remember the first grid point x is equal to 0. Sine 0 is 0. What is cos 0? That is 1. And this is what sine, whatever the grid point is. So this is sine 0.7143. This is cos 0.7143. Next is 1.4286. So this is sine 1.4286. And this is cos 1.4286 and so on. This is how we initialize. Okay, I'll just close this for you. So again, I'm telling you, this is the MATLAB keyword. This could be any function. You can just name any function. And it is not necessary that it has to be sin x cos x. You can even give constant values also. That is completely fine. So if you're telling that, okay, let t be a constant value 10, then what is the derivative of 10? Since 10 is a constant value, derivative will be 0. I can do that also. That is completely fine. Now, let me go back to the part one question. So I have done all the subsections. I have the ODE function. I have the boundary value function. I have initialized also. Now I run this code. Clear CLC. I'll just run this section by section. This is the most important part of the code. Once you have understood this, like it is pretty easy. Just a second. Yeah, run section. I've run the section here and I get the solution SOL. And again, SOL is a structure. Here you'll see the X values, which is nothing but the mesh I gave earlier. And I have the Y value, which is a solution. So if the Y value, if you see, the first row that you get will be the temperature. And the second row that you get will be the temperature gradient. The one thing they have to also always ensure, just for your understanding that, okay, the solver is giving me the right answer, what you have to check is, you have the boundary values given to you. Check if the boundary values are right. So here, this corresponds to the x0. X is equal to 0. And here temperature, I know. So it's a temperature 298. Was that given to me in the question? Yes, it is 298. Again, let me go to the other end of the road. At the other end of the road, here the temperature is given as 1.023 e raised to 03. That is 1023. Was the temperature given to me at the other end of the road? Yes, it is right. So here, this are satisfying the boundary condition. Remember, the first row gives you the temperature, and the second row gives you the gradient of temperature, dt by dz. So if I want to plot just the temperature, what I do, I write sol.x. Basically, I extract the x values from the structure, and I write sol.y. But in y, there are two things. I only want the temperature. So that is why I write first row, all the columns. That is first row, all the columns will give me the temperature, which will be in Kelvin. I want it in degrees Celsius. So I minus 273 from it. And I have X label, Y label. And this is how I can save a particular figure in the PNG form. Okay. So let me just run the whole code. So this is the solution that you get. Remember, at the one end of the road, so I can't zoom it actually, but at the one end of the road, it will be 298 degrees Celsius. So it will be 25 degrees Celsius. And the other end of the road, it will be 750. You can see here, it will be somewhere close to 750. Why can't I actually tools? I'll just write the data tips. See, it is 0, 25. And at here, it will be x is equal to 10, which is length of the road. And the temperature value is 750, which is given to us in the question. I hope this part of the question is clear. Now going to the second sub question. Now analyze the effect of ambient temperature condition. So if you remember, where is this ambient temperature condition coming in the whole code? So this ambient temperature condition, basically the T infinity only came when we were defining the ODE function. So that is where we have three subparts. One is the ODE function, then is a boundary value function, and then is the initialization part. So here the ambient temperature thing, and we coded it in the ODE function. So what we have to do is, if we have to study the effect of it, we need to code in such a way that the ODE function can take different ambient temperatures and play around with it. So let's do that. So that will be the part 2 of the code. So this we have already done, like how can we loop over a certain variable? We have like already done that. So I'll be doing the same thing here. Let me just consider an ambient temperature varying from -50 to 200 degrees Celsius and converting into Kelvin because the units has to be right. So I am just adding 273 to it. And I want to have like in between, I want to have 75 divisions. Okay. So that is why I use this colon operator from -50 to 200. So this is a range I'm trying to study for. Now what I do is I loop over each of the T ambient conditions. So first I'm taking for I equal to 1 to length of the T amp. And then I'm extracting a particular ambient temperature. So the particular ambient temperature based on the index will be extracted here. Now what I do, I give that ambient temperature to BVP sol. BVP sol is a different function. Okay, so this is a function that I have written here. BVP sol will take this ambient temperature as input and I'll be getting a profile and a position accordingly. Okay, this I'll come to later. So first, let's see what this BVP solve does. So now going to the BVP solve, it will take the ambient, a particular ambient temperature as the input, and then you will have an X mesh. This part of the question we have already done in the first part. This is the same. The code remains the same. So now, okay. So what I do is I read a particular ambient temperature value and my X meshing, I'm having the same meshing. Initialization of the solution is also the same. And here, instead of everything remains the same except this, the function, the ODE function that I'm calling. So the ODE function that I'm calling earlier only had two inputs, which is X and Y. But now I have X, Y, and I have this T ambient, this instant ambient condition also as the input. So this is something that is added. Only this function has been changed. The boundary value function remains the same. Initialization also remains the same. Now, what is the position? I'm just extracting sol.x to be the position. And what is the profile? I only require the temperature profile. So among the solution, there is y value, which will be the output, out of which the first row will give me the temperature, and the second row will be giving me the gradient of temperature. So here I only take the first row, which is the temperature value. Okay, so that will be the position and the profile which I'm outputting. So basically, for a particular ambient temperature, I'll be getting the position and corresponding temperature. That is the output of this section, the position and the corresponding temperature. And I plot it here. I have to again minus 273 because I am plotting it in degrees Celsius. And I hold on, which means I plot for one ambient temperature, I plot the temperature profile. I stay on the same figure. Again, loop over the second ambient temperature, go to the solver, solve for that particular ambient temperature. Again, plot that temperature profile. So what happens for different ambient temperature, the temperature profiles will be plotted on the same graph so that you can study how it looks like. Then I have the X label value, Y label value that has been added. Now I'm just, for your understanding purpose, I'm just adding a arrow. This you can see how to work with this. I'm just adding a vertical arrow just to see how the temperatures are varying. Or else you can just add labels and figure it out also. It's completely fine. And I'm saving it as a PNG file. See, these codes are already there in your recorded lectures. I'm just trying to explain it so that in case you have doubts, you can ask me, and we'll be solving similar problems in the problems I'll be giving after this. So now let me try to run this code. Okay. What I'll be getting will be like this. Positions, profile, which is me the temperature. For the first T ambient condition, for increasing value of T ambient condition, this is what I'll be getting. So this will be for -150. And when I increase the T ambient conditions, the graph goes up. The temperature profile keeps going up. Okay, again, the nonlinear behavior is there, but you can see how the temperature is varying, how the temperature profiles are varying when you increase the T ambient condition. Okay, is this clear to you? A very small thing is, like since the T ambient condition, if the T ambient condition is like very, very low. For example, the blue one, if the T ambient is very low, which means what will happen, there will be like a more convection that is happening due to the larger temperature difference. And because of that, you will be having a faster drop in temperature. That is why you see there is like this blue is having a faster drop in, like faster variation in temperature. On the other hand, when the T ambient condition is increasing, it will be the temperature change, the slope of how the temperature change will be like almost like a straight line. When the temperature T ambient is like going lower and lower, you will have a more steeper behavior in the temperature value. Okay, this you can observe, like you can keep increasing the temp. Here we have tried for -50 to 200 degrees Celsius. You can try it for even a bigger range and understand how the system behaves. I hope that part of the question is clear. Now moving on to the next part, that is repeat the above for different values of beta. So this is again similar to what we did for the T ambient. Just a second. Here what you have to do is, instead of looping over T ambient values, here you loop over the beta values. How do you write beta? Beta has to be varying. Here I'm using a small h value. Sorry, this was h value. Okay. Earlier, I think I set it as the grid points. This is the h value. Okay. Step size value that you take. You take 0.1 as the step that you want. Again, you loop over values of beta. A particular beta value is extracted here. And I give this beta value as an input to BVP solve. Again, remember where was this beta value coming? This beta value was also coded in the ODE function. So here, only this part of the question changes. Everything else remains the same. BVP function, instead of earlier I had a different function. This was my earlier function. Right now I have a different function altogether. Okay, oh, sorry, did I show you this part? So the function BVP function T ambient looks like this. Earlier it only had two inputs, X and Y. Now it has X, Y, and T infinity. Instead of fixing a T infinity value, it takes from here. Now have a different function which takes in beta value. Here what happens? I take a beta value that is being stored here in H, but the other T infinity value remains constant to be 298 Kelvin. Okay, which is 25 degrees Celsius. So this is how we input beta and you change the ODE function. So now for a particular value of beta, I solve this BVP solver and I get the position and the corresponding temperatures. I plot it, I hold on the same graph, take the second beta value, again solve the BVP solver, and I hold it on the, I get it on the same plot. So just in case if you want to see, this has not been shared to you in the recorded lectures, this code. So in case you want to see, you can just take a screenshot of it. So let me just run this code for you. So this is how the function looks like for increasing value of beta. So increasing value of beta means your beta was initially 0 and then it went up to 1. So when beta equal to 0, you will get a straight line. Okay. So try to see what the beta value is. I have one question like that in the today's problem solving. That is why I'm not explaining it right now. So when beta equal to 0, you'll be getting a straight line. You can see, actually, you can say that there is no convective effects there. Now, when beta value is increasing, there is more convective effect coming into play. So because of that, you will be getting this nonlinear behavior, whatever is there. And it will be steeper and steeper. It will go on steeper and steeper. So this is for increasing value of beta. So this is the code. In case, as this is not shown in the recorded lectures, I will show you once again so that you can compare your codes with it. And this is the function. The rest of the functions which has the boundary values. And also the initialization part remains the same as been shown to you in the recorded lecture. Okay, now moving on to the next part sub question of the problem. That is, earlier we had a particular boundary condition, right? That is, this T0 is equal to 25, T at 10 is equal to 750. Now we have to do for two more conditions. That is, first a point temperature value is given, and the second point we have the gradient value given. And in the next sub question, both the gradient values are given. So for coding this part of the sub question, what do you do? So there are three functions that we wrote. The first function for ODE solvers, second function ODE function, second function was for the boundary conditions, and the next was for initialization. So what you have to change is there's the boundary, the function that is having the boundary conditions. And how do we solve it? It's pretty easy because I've already explained that to you earlier. So everything remains the same. Okay, this part remains the same. What is this? This is the case one. Basically, the question we were solving the first part of the question. This code is the same of as like this. This code is the same. Okay, this and this code is the same. You take the BVP initialization, XMS, and the guess you're given. Here you have the function here, and this is a boundary function. Let me just again show you the boundary function. This is a boundary function. Sorry, this is the BVP function. Yeah, so this is the boundary function here. Yeah, this is the boundary function here. Temperature at the first point is minus 298, and temperature at the first point minus 1023 is equal to 0. Basically, the two conditions has been written. Now, let me just close all of it. Okay, now the next case, what we have is we are plotting it, we are holding it on. Okay, and the next part of the question is we have a function value at the first point and a derivative at the second point. So for that, the ODE function remains the same, initialization remains the same, but the boundary function I'm changing. So it is BFC CN2. That is my next function. So what do I do? Here, the first condition is the same, right? The temperature at the first point is minus 298 is equal to 0. But in the next part, what happens? I'll just show it to you again. I hope you remember what I said. YA is there, which will have two values, sorry, temperature and dt by dz, which is nothing but sorry, dt by dx. I think I should increase this. Yeah. So this similarly you have YB also. Okay. So in YA, which means the starting point, you know this value. Okay. In YB, you know the second entry. So what do you happen? What happens here? The index has to be varied. Okay. The gradient at YB, which is the second index, is equal to 473. You bring the 470 to the other side so that you can write it in equation format. So you write YBF2 minus 473 is equal to T, is equal to 0. That will be a boundary condition value here. Now, you going back to the question, that's the only change here. Again, you plot the solution. Now, the coming to the third boundary condition where both the gradients are known. So right now, I hope you would have understood the trick. What you do, you change the index. YA2 minus 273 equal to 0 and YB2. Here, both are referring to the gradients at YA and YB minus 473 equal to 0. Okay, so this is what you do. Now, let me just run this part of the code. And one other thing is there are this boundary conditions are called as Dirichlet boundary condition, mixed boundary condition, and Newman boundary condition. I'll just show you how this works, but first let me just run this code for you. Okay, this is how it works. The black one is what we saw earlier, the first part of the question, that is Dirichlet boundary condition. Now, if you have mixed boundary condition, which means you will have a function value and a gradient value given to us. So that is a red one that is there. You can confirm the function value here. See here the function, here it is 25 degrees Celsius, similar to the first black curve that is there. But here you have the gradient to be a different value. If you want, you can just calculate the gradient here numerically and confirm if it is right. Next, you have Newman boundary condition, where the gradient here has been given to you, gradient here has been given to you. Both gradients are given. So there are several boundary conditions like that. So I'll just show you here. Yeah, Dirichlet boundary conditions. When it's the first part of the boundary, second part of the boundary. In both the places, if the function value is given to you, it is called as Dirichlet boundary condition. If in both boundaries, if the gradient value is given to you, it is called as a Newman boundary condition. If on both the cases, you have a combination of the function value and the gradient value to be given to you. Okay, it's not directly a function value or a gradient value, it's a combination of that. A equation combining both, then it is called as a Robin boundary condition. Now, mixed boundary condition means in first part you have if you have a function, and the second part if you have a something like a mixed condition. So this could be vice versa also. That is, first part you have a gradient something, second part you have purely the function value. Then this is called as mixed boundary condition. And Cauchy's boundary condition means at both places you have, both the function value and the gradient value. Okay, so these are the different boundary conditions that are available. So that's it. I hope you understood how the system behaves. Just wait, give me a second. Let me just check the time. Any questions? Okay, I hope there are no questions. Now let us move to the problems then. I've taken it from previous year assignments and like various sources. It will help you. It will help you with your assignments. So I'll just show you the questions. I'll give you a few minutes. Once you've got the answer, please put it in the chat box and then we'll discuss. So this is the first part of the question. I'll give you 2 minutes. Please put the answer in the chat box. Any answers for this? So in a composite rod made of two different materials in series, the overall thermal resistance is, see, the series and parallel, whatever resistance formulas we have learned, that formula applies here also. So if we have thermal resistance in series, it will be R total will be the sum of the individual resistance. So R total will be given as R1 plus R2. So option A is the correct answer. Now moving on to the next question. It is a MATLAB problem. So please open your MATLAB and try to code this. And I'll and I'll explain the question and show you the solutions within few minutes. So let's try to solve this problem. So we have like a second order BVP in MATLAB using, we have to solve this BVP using MATLAB functions. So for this example, use this function like y double dash plus y is equal to 0. We have an interval that is defined from 0 to pi by 2, subject to boundary conditions that is at pi by 2, at y equals y at, I think it is the independent variable is x. So y at x is equal to 0 is 0, and y at x is equal to pi by 2 is 2. The initial condition for y value has to be sin x, and initial value of y dash value has to be cos x, similar to what we did earlier. Temperature initial value is sin x, and derivative of temperature initial value is cos x. We have to use a BVP file C. For that, you need to write a function that represents the equation of the first order equations, and then you have to write a function for boundary conditions. Then you have to write a function for initial guess. Then use the BVP solvers using all threes to solve this question. This question is pretty simple, but let's try. Let me just show you the answers. So first, So first, this is the thing we have. So I have from 0 to pi by 2, that is my limit. And I am gridding it by, I need 5 grid points. Okay, so that is what linspace is doing. Now I'm initializing the solution initial values using BVP INIT, which is an inbuilt MATLAB function. I'm writing for each of these grid points, my initial value should be given by guess. So guess is what we have already seen earlier. I will not change the function. That is, if you take a particular x value, the first initial value, that is the first row, should be initialized by sign x, that is corresponding to, earlier it was corresponding to temperature, here it is y and y dash. So corresponding to y, it has to be sin x, and corresponding to y dash, it should be cos x. This is my initial value function. It has to be a column vector that is given as an output. So that part is also done. Uh, if you want, you can just write dot. It's the structure, right? So if you want to see how the x and y values are there, you can explicitly write it here, or it's okay. I think you guys know by right now how this is there. Now I'm using calling the BVP solver. It has the BVP functions. So let me just show you the BVP function. So this is what is there. I've tried to see. Okay, so BVP function is I initialize it to be a column vector. You can need not initialize also, that is completely fine. Now what I have is, so let me just write the equation first. What I have is y double dash plus y equals 0. So it is double dash, okay. Now I write y double dash is equal to minus y. Now this is in the form of the d square t by dz square is equal to minus gamma t minus y. Okay, that is how this looks like. Now what I do, I take y dash to be, that is dy by dx as some new variable. And okay, dx, okay. I don't know why I keep writing z is equal to, I'm giving a new variable, maybe something q. And I'm writing dq by dx to be equal to minus y. So this will be my first equation. This will be my second equation. How do I write it? What is q? Q is nothing but if I have a vector like this, my first entry will be y, and my second entry will be dy by dx, which is nothing but q. Okay, this is how my output vector should look like. So in my output vector, q means it's the second entry. So that is why I write here. In my output vector is capital Y. Okay, this is my capital Y. Capital Y second entry q. That is what is written here. Q. And my next equation will be minus y. What is minus y? That is my capital Y's first entry. That is why I write minus y, in the bracket I write 1. So I have properly written the equation here. Now I need the boundary functions. Remember the boundary function, it has to be, it is the display boundary condition itself. The first boundary condition is 0. So you just write y0. Again, remember, I have here two values, y0, okay, which has two values here, y and q. And I have, maybe I write it here itself, y1, which has y and q. Y0 means the first boundary condition. In that, I'm taking the first index and telling it is 0. Okay, minus 0 is equal to 0. And in the second boundary condition, also I have the y value. So in that y1, in the bracket 1 is equal to 2. I bring the 2 to the other side to write it in the form of an equation. So that's how I get this. Now this is a guess function. Sorry, I showed you the previous one. Okay, actually, if you write the function like this, here this will go access to this one, whatever is written inside this script. So you get sin x and cos x that's been written. Now we solve using the BVP solver. You extract the x and y values. I only need to plot the first values, that is y. So that is why I write sol.x and corresponding sol.y. Out of that, I only take the first row. That will be corresponding to y. Okay. Let me clear all the items and I'll try to run this. Just a second. So this is how it looks like. It is y versus x. This is the curve. It looks like this. There is like a large intervals because I have only given 5 grid points. If I want, this is because I've given only 5 grid points. If I want like a smoother curve, I give like 15. Let's see how it works. Okay, then I get a smoother curve. So there are 15 grid points. So then you get a smoother curve. But at every point, the value remains the same. Like the if I give a 5 grid point, a 10 grid point at x is equal to 2, the value will be the actual y value itself. Okay. Just that your graph will not look smoother. Now let me just clear this off. I hope you got the answer. Now showing you the next question. What is thermal diffusivity? Basically, what is beta? So basically, the beta value is called as like thermal diffusivity. You can also use usually use alpha value for describing it. So the equation for beta is basically K by rho Cp, that is conductivity divided by the rho Cp, where Cp is the specific heat capacity at constant pressure, and rho is the density. Okay, so that is a term that you get. Beta is equal to K by rho Cp. Now coming to the next part of the question. For this also, you'll have to use MATLAB. You have the ODE equation given to you in the first line, that is y double dash plus 2 by x y dash plus 1 by x raised to 4 is equal to y. So when you're first coding it, what you have to do is you have to take those whole two terms to the other side. And the interval which you're looking for is 1 by 3 pi to 1. And the boundary condition has been set at x is equal to 1 by 3 pi, your y value is 0. And at x is equal to 1, your y value is sine 1. Initialize all the points as 1, 1. So that is another thing that you should keep in mind. And compare with the analytical results. Analytical results has been given to you. Your first y, from your y, you get two values. One is y and one is y dash. Your y should correspond to sine 1 by x and y dash corresponds to this analytical function. So what you have to do, first solve it using this ODE solver, BUP5C. Then also try to plot this function on top of it. So I'll just give you a few minutes and then we'll discuss the answer. So let's see the code for this. So first we have the mesh that I've created from 0 to, sorry, this is part 4 of the question. Yeah. So here my grid is from 1 by 3 pi to 1. I'm dividing into 10 grids. And for initialization, what I do is earlier I gave a function because the function value is different at different points. But here what I'm doing is I want the whole function at like every grid point to be saved as 1, 1. So that I can give that directly here. Okay, 1, comma 1, 1 it's a column vector, 1, comma 1. So I'll just run this for you and show you how it looks like. Evaluate the selection. You will have a solution like this, where the x value is a grid system and your y value will be like this. It will be all ones. See, it will be all ones. Now what do? You have initialized that BVP function. Now we need to have the function for saving the ODEs. So it will look like this. Should I explain to you one by one? Just a second. Let me just write down the equation is like a bit tricky. So here, just imagine that I'm taking everything to the other side. So this will be minus and this will be minus. So I'm writing y dash is equal to a new variable, let it be t. Okay. And dt by dy, which is nothing but y double dash. Okay. So this is nothing but y double dash is equal to, we'll have minus 2 by x. So minus 2 by your x value. You have y dash coming. What is y dash? You know that is the first term. So if you have like a main vector y, it will have two terms. First will be this first equation, that is dy by dt. So the first variable I'm solving for is y. And the second it will be dt by dy. So that is t, which is nothing but dy by dt. Okay, please, sorry, which is y double dash. Just a second, am I writing it right? Oh, sorry, it has to be x. Just a second, let me just erase this. I'm writing dy, first one, dy by dx. So my first variable is y here. Second variable is t. Okay. And that is equal to t. T is nothing but that will be basically, if I have a y variable, I'll have to write y. Sorry. That will be basically y and write 2 here. And here it will be minus 2 by x and y dash will be nothing but t, right? So that will be y 1 minus 1 by x raised to 4. Y will be again, what is y value? That is y of 1, right? Y of, sorry, this has to be changed. Y dash is what? Y dash is t, right? So it has to be 2 here. Sorry. This is how it looks like. Minus 2 by z, y of 2 minus 1 by x raised to 4, y of 1. Make sure you don't make a mistake like this. I'll show you MATLAB just to confirm which is right. So that will be y of 2 minus 2 y of 2 by x minus y of 1 divided by x raised to 4. So this will be the equation that we have. Okay, right, it is a column vector. Now we have to write the boundary condition. Again, I'm not repeating again and again because both are given as the y value itself, because of that the index is always 1. We are, or what we have is a display boundary condition. So index will be 1. First value boundary condition is 0. Second boundary condition is equal to sign 1. You take it to the other side, so it become minus sign 1 equal to 0. Okay, so here also, this also you write as a column vector. Now what I do is I clear and I just run this problem. I show you how does it look like. I have two plots. Why do I have two plots? If you see this thing, I have written the analytical solution also. So I get the solution from here. From the solution, I am plotting. This is the analytical solution for the first output. Okay. Sorry, the first analytical, this is y value. This is y. Uh, just a second, what am I plotting? Sorry. This is the x grid, and I'm plotting the actual function, which is the first analytical solution that is given to me. I have to compute it for every x1. And on the same graph, I also have the solution that is got from by BVP5C, and I take the y values. Now in the second figure, what I plot is I have the x plot, and I get the y dash that is calculated analytically using this formula. Then I also plot the x value and the corresponding second row, which is basically extract the y dash for me. Okay, so I'll have two figures. Now going to the figures. This is the first figure corresponding to y value. The line that you see is what we got from the BVP solver, and the circles that you see is what you got from the analytical solution. As you can see, both are perfectly matching. And this is the graph for y dash, which is the gradient of y. Again, you can see the black solid line is what you get from the BVP solver, and the circles that you see is what you get from the analytical solution. That also you can see it is like perfectly matching. Is this clear right now? Oh, sorry, it's the other way around. The analytical solution, it is by the solid line, and the BVP solver, that is what is given in the circles. Okay, so it's the other way around. But anyway, both are the same values. I hope it is clear. Do you want to see the code? I hope it is clear. Now moving on to the next question. For a road with constant K, the temperature distribution is steady state. In a steady state is, this we've already discussed. If it's a constant K, the temperature distribution will be a linear. It will be of the form AX plus B. This we have already seen in our previous lectures. I hope you remember this. Now moving on to the next question. For a copper rod, L equal to 2 meter, D equal to 0.02 meter, K equal to 400 watt per meter Kelvin. We have two temperatures given at the two ends of the road. T1 is at the one end of the road, which is 150 degrees Celsius, and T2 is the other end of the road, 30 degrees Celsius. What will be the heat transfer rate? Remember, only K value is given, so you should be able to find the value for it. You don't have to use MATLAB. If you remember the heat transfer equation, you can try to solve this. I'll give you like 2 minutes and then we'll discuss the answer. So this is the equation for heat transfer Ka T1 minus T2 divided by N, where K is the conductance equation, conductance that is for K equal to 400 watt per conductivity or for 400 watt per meter Kelvin. A is the area of cross section, so that will be pi r square. Um, so your diameter is 0.02, so your radius will be 0.01, half of it. So pi r square will give you this value, 3.14 into 10 raised to minus 4 meter square. Now T1, T2 minus T2 will be the temperature gradient, that is 150 to 150 minus 30 divided by L. So basically you'll have to put all this into this equation, and finally you will be getting 7.536 watt, which is option C, close to option C. I hope you got it. Any doubts? Let's move on to the next question. In Fourier-Heat's law, the heat flux is equal, sorry, heat flux is directly proportional to or whatever is true here. So Fourier's law of heat transfer. So here what happens is the heat flux is along the decreasing direction of T. So that is the right answer because Q is given as minus K in the temperature difference. So it is proportional to the temperature, but it is the negative. It is along the negative direction. So the heat flux occurs in the direction of decreasing T. That is option C is the right answer. Now moving on to the next question. Again, you have an ODE solver. So ODE, you have to use the BVP, not BVP5C. You have your boundary value problem. You have an equation like this: x is equal to minus x is equal to 1 by 4. You have to use finite difference. Okay, so that's what is required here. Our grid values contain total 5 grid points. Okay, there are 5 grid points. For the first grid point, the value is 0, and the second grid point also the value is 0. So last grid point also value is 0. You have three interior grid points, x1, x2, x3. And because of that, there are two unknowns, that is u value at x1, u value at x2, u value at x3, which is called as u1, u2, u3. So you use finite differencing, you will be getting a matrix in the form of ax is equal to b or something, and then try to solve for u1, u2, u3. Okay, please try to do this. This might be a little bit tricky because we have not done any solved examples with it. I've just shown you one example. Like, I'll discuss it in like two minutes. Please take a pen and paper and try to make the grid yourself. So let's try to solve this. So this is how, if you write it is a double derivative. So you can use the central difference formula, whatever I showed earlier. Finally, we'll be getting your answers like this. 2u1 minus u2 is equal to, here there will be a denominator h square, which will go to the other side. And here h square will be 1 by 4 square, which will be 1 by 16. So it will become pi square sine pi. First x will be 1 by 4. So pi by 4. And this is 1 by h square. That is why there is 1 by 16. And the second grid point, this is how it looks like. Minus u1 plus 2u2 minus u3. Again, h square going to the other side. And here the x value will be pi by 2. Here x value will be 3 pi by 4. And here the equation will be minus u2 plus u3 is equal to this. So you have got three equations like this. Next step is you have to write the three equations into a matrix format. So first, for not making a mistake, first let us write the u1, u2, u3 properly. This has been written. And the b1, b2, b3, this also can be written. Since pi square by 16 is there in all the thing, let us take it outside. It will become sine pi by 4, sine pi by 2, sine 3 pi by 4. Now let us see to write this. So here u1, u2, u3 means here this will be in the order of u1, u2, u3 coefficient. This will be u1's coefficient, this will be u2's coefficient, and this will be u3's coefficient. And this will be equation 1, equation 2, equation 3. So here it will be 2 is the coefficient, minus 1, there is no u3, so the coefficient is 0. Second equation, u1's coefficient is minus 1, u2's coefficient is 2, u3's coefficient is minus 1. And in the third equation, u1's coefficient is 0, u2's coefficient is minus 1, u3's coefficient is 2. So we've got the coefficient matrix. Now the only thing we don't know is u1, u2, u3. You have to inverse this and multiply. Finally, you'll be getting the values like this. Is the answer clear? I hope it is clear. Now moving on to the next part. For convective boundary conditions, the heat flux is proportional to, I'll give you 1 minute. For a convective boundary condition, the heat flux is proportional to what is the temperature difference between the surface and the fluid, which is basically your whatever the surrounding temperature is. It could be a fluid, it could be air, whatever it is. So the temperature which between the surface and the surrounding temperature, surrounding fluid. So this is Newton's law of cooling. So option A, T surface minus T fluid is what that will be driving the convection. Now coming into the next question. So this is a very long numerical question. I'll just give you a quick glance into it. So we have an energy balance equation for a heat generating fluid given in a plug flow insulated pipe of length L. So this is the equation that we have. It's a second order ODE. You know what theta and you know what gamma is. This will come to that later. So the coordinate x is a direction along which the axis of the pipe is there and temperature T is there, which is only a function of x. Okay, so there is only, it's a single ODE equation. T0 and TL are the temperatures of the inlet and outlet pipe respectively. And term Q is related to the heat generation where RE is Reynolds number and PR is the Prandtl number. Now we have the boundary condition that is at gamma is equal to 0, gamma is equal to 0, we have theta equal to 0, gamma equal to 1, again we have theta equal to 1. So this is the Dirichlet boundary condition. We are given the Prandtl number value, Reynolds number value, Q value is given. We should be able to solve this using BVP 5C and plot theta versus gamma value. So let's quickly go to the Matlab. So all the constants I have first written. Now I have to write the ODE function. So the ODE function, should I explain it like once again? Uh, so first I'm writing d theta by d gamma to be equal to a new variable. Here I am taking maybe z. Okay. Now I'm writing d z by d gamma. What I do is I take this whole term here and I have to also multiply it by the Prandtl number. So that will be the Prandtl number multiplied by what is there. So I'm not writing everything. RE remains the same. Reynolds number remains the same. And d theta by d gamma, that is nothing but your z. Okay. Plus q times theta. So now what will it be? If you have a capital Y like this, the first value will be theta, second value will be z. So this will be y of 2. So here it will be y of 2 and here it will be y of 1. Remember that and we'll check it again. Y of 2, y of 2, y of 1. Let me share Matlab. See, this is equation. Y of 2, Prandtl number multiplying Reynolds number multiplied by y of 2 and q multiplied by y of 1. So this is a ODE function. This is a boundary value function. It is Dirichlet boundary condition. So both the indexes will be 1. Okay, so we only know what is the value of theta. Here initially it is 0 and next it is 1, which you take it to the other side to make it -1. This is my initial mesh that I am making. From 0 to 1, I am making 10 grid points. I initialize all the grid points. Here the initial theta value is declared as 1. and the d theta by d gamma, that I am declaring every point to be, sorry, first to be zeros and second values to be ones. So first row will be all zeros and the second row will be all ones. I'm using the BVP solver. Then what I'm doing is, I have the BVP solver and trying to plot it. This part of the question, if you want, you can do. That is what I'm doing is I'm creating a finer grid of 0 to 1, and I'm just extrapolating the values. You can use deval or also for extra in interrupt one we have already seen in the previous lectures. That can be also used. And then you calculate the gradient, and wherever the gradient is tending to 0, that will be the point where the system has reached steady state. So our question is we need to plot the theta versus gamma and also identify at which point the system will reach steady state. Or else you can directly plot it and visually see it from the graph. So let me just run this code. So this will be the question, showing it to you again. So you'll get somewhere close to, so this is what the temperature profile looks like. That is somewhere close to 0.2, 0.3, it will start to become a steady state value. Okay, and it remains in the steady state value, which is 1. Boundary conditions, you can see one end it is 0, the other end is 1. So let's see, the answer will be, correct answer, the temperature at which, sorry, the theta value at which it will be, system will be steady state will be, it depends. It will be 0.3804, given that the gradient has to be below 1 e raised to minus 2. You can make it even stricter. You can make it 1 e raised to minus 4 or minus 5 or whatever it is. That is how you get the steady state theta value. Is this clear? Okay, let me just close this then. Moving on to the next question. Boundary condition at an insulated end of the road will be, I'll give you 1 minute. The answer is at the insulated end means there is no heat transfer. Heat flux is not there, so heat flux is equal to 0. Option B. Now, because there is no time left for us, I'll just go through the questions and answers one by one. I'll give you the PPT so that you can take your own time and try to analyze each answer. So the steady state material balance for diffusion is given a catalyst pellet in a spherical catalyst pellet leads to the following boundary value conditions. It's a second order boundary the ODE equation. C is a dimensionless concentration, R is a dimensionless radial position, theta is the tail modulus, and N is the order of the reaction. Boundary conditions given as R at R equal to 0, we have dC by dR is equal to 0. And at R equal to 1, we have C equal to 1. So the options we have is the problem has a Dirichlet boundary condition at R equal to 0. The problem has a Dirichlet boundary condition at R equal to 1. The problem has a Newman boundary condition at R equal to 0, and the problem has a Newman boundary condition at R equal to 1. Which will be the answer? So the answer is this. That is the Dirichlet boundary condition means a function value will be given. That is given as R equal to 0. So the problem has a it is given as R equal to 1. Okay. So at R equal to 1, there is a Dirichlet boundary condition, that is option B. And at R equal to 0, we are given the gradient. This means it's a Newman boundary condition at R equal to 0. That is option B and C. Dirichlet boundary condition at R equal to 1 and Newman boundary condition at R equal to 0. I hope this is clear. And steady state, if T1 and T2 are at the two ends, now what will be the temperature gradient? Any answers? The temperature gradient, if you remember, it has to be the heat flow has to, the question, I think there is something missing. It has to be along the negative temperature, right? So what you will do is it will be T2 minus T1 divided by L. That is option B. Now consider a boundary value problem. D square y by dx square plus dy by dx is equal to 2y. And at x is equal to 0, y value is 0. At x is equal to 1, y value is 1. Now plot the solution that exhibits how y is varying with respect to x. Okay. So for that, what you do is you'll have to solve this ODE, plot y versus x curve, and see how this y values vary. It's a simple ODE equation, so I think I'll directly show you the code. So this is the ODE equation. I'm first initializing everything using I'm using 11 grid points between 0 and 1, and I'm initializing it using guess, which is nothing but sin x and cos x. You can take different one also. For example, I can take the first guess to be x, and the gradient of x will be 1, right? So like that also I can take, that is completely fine. Now what I do is I have initialized, now I have the ODE function. So for the ODE function, I go here, sorry for that. So this is what y1 is equal to y, and your y2 is nothing but, so it will look like this, the equation. Okay. So here you will have y2, and this will be 2 times y1 minus y2. If I want, I'll just write here. And right for this one also, I'll just write. Okay. The equation is y double dash is equal to 2y minus y dash. Let me just write a new variable. Okay, that is y dash is equal to a new variable, that is t. Okay, this is what, and now I have y double dash is equal to, that will be basically this part, that is 2y remains as such minus y dash. What is y dash? That is t, right? Okay, so this is first equation, or else you can say this is t dash, right? Okay, this is the first equation, this is the second equation. So if I have a vector y like this, it will have two inputs. The first one is dy by d. So it will be y here. And the second is t is the variable. So here it will be capital Y, in bracket you have t, which is the second index. Here it will be capital Y, and y is in the first index. And again here it will be capital Y and the second index. I hope this is clear. So it will be y2 minus, the next equation will be 2 times y1 minus y2, whatever we have derived here. I hope this is clear. So now we have to write the boundary condition, y of 0 is equal to 0. Since it's display, both the indexes will be 1. And you take the 1 to the other side, y of b1 is minus 1 equal to 0. Now let me just, I have the solution here. From the solution, I am just taking, I can directly write sol.x and sol.y. That is also completely fine. Okay. Here I'm just plotting it. Okay, this is a behavior I'm getting. You can just cross check whatever you're getting with the code. Okay. So now among the options, what is the answer that we have? Directly, y is directly proportional to the square of x. No, if it's a square of x, you will got a nonlinear behavior with respect to x. It is inversely equal to square of x. No, that is also not true. Directly as x, yes. As x increases, your y value also increases. You got a increasing straight line. So the option C is your answer. I hope you got this right. Again, once more, I can show you the MATLAB equation, MATLAB solution. This is how the equation looks like. Now going on to the next question. What is the steady state condition in heat conduction? We know that steady state means there should not be any change with respect to time. So that is the first, that is the option B. Temperature does not change with respect to time. Otherwise, dou T by dou time, that is equal to zero. Change of temperature with respect to time is equal to zero. Which of the following has the highest thermal conductivity? Obviously, we have learned that metals are having highest thermal conductivity. So among whatever is given, water, glass, copper, wood. Since copper is a metal that is having the highest thermal conductivity. What signifies the thermal conductivity? What do you mean by the term thermal conductivity? So it means the rate at which the heat passes to the material. Conduct means the ability to transfer the heat to that material. K indicates the ability to conduct heat. That is option C. Identify the incorrect statement from the following options regarding the assumptions of Fourier's law of steady state one-dimensional heat flow. The incorrect statement is this: material is anisotropic. We assume that in the Fourier's law of steady state one-dimensional heat flow, that the material is isotropic. That's the thermal conductivity is same throughout that particular material in all directions. So it is isotropic. That is an assumption that is taken. So material is anisotropic, we don't consider that. So that is a false assumption that has been taken. Negative sign in Fourier heat transfer, heat conduction indicates what? Any answers? So what happens is heat always flow in the direction of higher temperature to lower temperature. So that is what the negative sign ensures. It goes from the flows down the temperature gradient. Next question. Thermal conductivity represents the amount of heat conducted across a unit area when the temperature difference is 1 Kelvin. Is that right? Yeah, this is right because you have the equation which we tried to solve earlier, where Q was equal to K, sorry, this has to be small letter K, delta T divided by L, right? So when, sorry, K is area was there. Sorry for that. Let me just write small letter way because it's space constraints. So if this A is unity, temperature difference is unity, the length also has to be, okay? Unity, then K is nothing but the amount of heat conducted. So that's the definition of K. So the answer is true. True, because that is the definition of the thermal conductivity K. Now, most metals are good conductors of heat because they have free electrons. That is what makes the metals a good conductor. Now, I think this is the last question. So, mark the material which has the least amount of thermal conductivity. So, air, because air we usually consider it to be a poor conductor or it's a good insulator. So, that's it with today's session. I hope this session was useful. I gave you some basic questions regarding the BVP solvers. Any doubts? So hope there are no doubts. So I'll be ending today's session. I'll be uploading the recording soon. So thank you all for attending session, and we'll have this another section on next Friday, 6 to 8 p.m. So thank you so much. I'll be ending the session now.